Wish you all. I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today I wish to tell about fundamental quantities of a crystal. Fundamental quantities of a crystal, and also we shall see this simple cubic crystal. Simple cubic crystal. So the fundamental quantities of a crystal structure. So the fundamental quantities are atomic radius, so coordination, number, atomic packing factor, or density of packing, or packing fraction also can call it. So fundamental quantities of a crystal structure. In this, first we shall see this atomic radius. Atomic radius. Atomic radius is the half distance between nearest neighboring atoms in the unit cell. Atomic radius is nothing but half distance between nearest neighboring atoms. Half distance between nearest neighboring atoms in the unit cell. Suppose if there is a unit cell, so the atoms are at each corner there is an atom. So the nearest neighboring atom to this is besides one, this one. So if the length is taken as A, that is, we can say edge length. So edge length of this unit cell. So edge length of the unit cell is A. So from here to here, the length is A. When taking atomic radius, so half distance between neighboring atoms. So neighboring atom is this one. So if I am taking this atom, the nearest neighboring atom to this atom is this one. So the nearest neighboring atoms, half distance between nearest neighboring atoms in a unit cell. So here to here to here is R. So edge length, we can say, if we take a simple cubic, all the sides, all the dimensions are same. So edge length is A. So nearest neighboring to this atom is this one, or we can take a nearest neighboring atom this also. So the half the distance between the nearest neighboring atom. So half the distance to the nearest neighboring atom to this one is half, here to here. So this is atomic radius. Atomic radius. So atomic radius is the half distance between nearest neighboring atoms in the unit cell. Or else here also we can take here to here. The radius is R. Atomic radius. Coming to the coordination number. Coordination number is the number of nearest equidistant. The number of nearest equidistant neighbors that an atom has in its unit cell. The number of nearest equidistant neighbors that an atom has in its unit cell. So nearest neighboring. So if I take a two-dimensional plane, suppose so the atoms are occupied like this. This is an unit cell of a 2D plane. Let for example So atom 1, 2, 3, 4. Atom 1, 2, 3 and 4. Here the edge length is A. Atomic radius is R. Atomic radius is R. So here to here the radius is R, or half the distance between the neighboring atoms. Half the distance. So here to the neighboring atom for this first atom is can take a 2 or 4. So here to here is R. Atomic radius, half the distance between nearest neighboring atoms in the unit cell. Now we are talking about the coordination number. Talking about the coordination number. So the number of equidistant, that is the number of nearest equidistant neighbors that an atom has in its unit cell. So how many number of atoms are there nearer in 2r distance? That is nearest equidistance to this first atom is this second atom and fourth atom. If we take 2D plane, the nearest equidistant neighboring atoms are 2 and 4. So the number of coordination is 2 in this case. 2 in this case. So its value depends upon the type of the crystal. So coordination number is the number of nearest equidistant neighboring atoms in the unit cell. So the coordination number is calculated by taking the nearest neighboring atoms at a distance 2r. So the distance 2r means from here to here, because here to here is r, from here to here is r. So totally 2r distance. So this is also 2r distance. If I am taking this first atom, so the nearest neighboring equidistant atom for first atom to the first atom is second and fourth, because these two only be at 2r distance. As here we are saying the coordination number is calculated by taking the nearest neighboring atoms at a distance 2r. Okay, but we couldn't take the atom of 3 as a nearest equidistant neighboring atom. We could not take third atom as a equidistant nearest neighboring atom. We couldn't calculate that. So the atoms which are at 2r distance can counted as nearest, that is coordination number. Can counted as a coordination number. How many atoms are at nearest equidistance? So here in this, the coordination number is 2. So in this case, the nearest equidistant neighbors of the atom is 2. That is coordination number is 2. Okay. So why we couldn't take third atom as nearest neighboring atom? Because here to here, if I am taking from here, to here, the length, that radius is r. Like the same, from here to here, the radius is r. So 2r distance, r plus r, 2r. and with 2R there is more space in between these two atoms, so that the distance to this atom, that is the first atom to the third atom, the distance is more than 2R. So we could not take the third atom as equidistant neighboring atom. We couldn't count in that way. We couldn't count as a coordination number. So neglecting this one, we are taking second atom and fourth atom the coordination number. So in this case, the nearest neighboring atoms to the first atom is 2 and 4. So that 2 is the coordination number. Density of packing. Density of packing or packing fraction. The ratio of volume occupied by all atoms in an unit cell to the total volume of the unit cell is called packing factor or packing fraction or density of packing. So, the ratio of volume occupied by all atoms in an unit cell to the total volume of the unit cell is called packing factor or packing fraction, or else we can call it as density of packing. So, mathematically, packing fraction is equals to V by capital V. V by capital V. That is, this V is, small v is volume occupied by all the atoms in the unit cell, and a capital V is the total volume occupied by the unit cell. Total volume of the unit cell. Okay. So, a high value of packing factor indicates that the atoms are very closely packed in the unit cell. A high value of packing factor indicates that the atoms are very closely packed in the unit cell. Packing factor is a dimensionless and is always less than unity. So this packing fraction is always we can call as atomic packing factor, also called as atomic packing factor. So it is a dimensionless quantity. It is a dimensionless and also it is always less than unity. Atomic packing factor is always less than unity. So this atomic packing fraction also termed as number of atoms number of atoms in an unit cell into volume of the atom, that is volume of the each atom divided by total volume of the unit cell. Okay. So that is number of atoms unit cell in the unit cell into volume of the atoms divided by volume of the unit cell. Can also write like this. Okay. So packing fraction is the ratio of volume occupied by all the atoms in an unit cell to the volume of the unit cell. So it is a dimensionless quantity and it is always less than unity. This atomic packing factor gives how much the atoms are packed, how much the atoms are packed in a crystal. So whether it is tightly packed or it is loosely packed. So if the atomic packing factor is getting a high value, then it indicates that the atoms are very closely packed, that is very tightly. Atoms are very tightly inside the unit cell or crystal. So why we are taking for the crystal, for the unit cell itself? Because unit cell is a repetition. Okay, they are a repetition. They are the building blocks of a crystal. Unit cell is a building block of a crystal. So that if we are taking for the single unit cell, then we can calculate for the entire crystal. Next, characteristics of a cubic unit cell. So what are the characteristics of a cubic unit cell? So the characteristics are volume of a unit cell, atoms per unit cell, coordination number, atomic radius, and packing fractions. These are all the characteristics of a cubic unit cell. Next, coming to the simple cubic crystal. Simple cubic crystal. So the unit cell of simple cubic structure, has atoms only at the corners of the cube. In the unit cell of a simple cubic structure, it has atoms only at the corners of the cube. So consequently, these atoms touch along with cube edges. Consequently, these atoms touch along cube edges. So this is a simple cubic crystal. Simple cubic crystal. So this is one unit cell. It is a one unit cell, small part of a solid. So this unit cell of simple cubic structure, atoms are only at the corners. Atoms are only at the corner. Only at the corner. So consequently, these atoms touch along cube edges. So these atoms touch along with cube edges. Okay. So this simple cubic structure is loosely packed. So in SCC, the atoms are loosely packed. Why it is loosely packed? Because each atom has only 6 nearest neighbors. Each atom has only 6 nearest neighbors. So the coordination number for SCC, that is simple cubic crystal, is 6. How we can calculate this coordination number for simple cubic crystal? So the coordination number is the number of nearest equidistant neighboring atoms in an unit cell. Okay. So the nearest equidistant neighboring atoms that an atom has in a unit cell. That is coordination number. Okay. So each corner atom has 4 neighbors. Each corner atom has 4 neighbors in the same plane one is vertically above and one immediately below. So giving like that a total number of 6 nearest neighboring atoms. So let's see how it is. This is simple cubic crystal. Now we are calculating the coordination number. Calculating the coordination number. So it has atoms at each corner of the simple cube. So 8 corners, each corners, so have 8 atoms. So each corner we have atoms. These 8 atoms can be shared with other unit cells. We shall see later this one. So simple cubic has 8 corners. So there are atoms at each corner of the cube edge. At the cube edge. So I am calculating coordination number. Coordination number is the number that nearest equidistant neighboring atoms that an atom has in its unit cell. Okay. So the number that nearest equidistant neighboring atoms that an atom has in its unit cell is the coordination number. Suppose if we take the nearest neighboring atom, suppose I am taking this atom. So for this atom, how many nearest neighboring atoms are there? How many nearest neighboring atoms are there? So the nearest neighboring atom will go into that. So also it can be taken as the atoms which are at 2r distance. The atoms which are at 2r distance to that atom, to that particular atom. Okay. So here this atom. So the nearest neighboring atom which are at 2r distance. Suppose edge length I am saying A because it is a cube. Wherever you can take the dimensions be the same. A is equals to B is equals to C. In that case, A is equals to A is equals to A. So, edge length is A. The atomic radius is R. So, R in that sense. So, here to here is 2R because half of the radius is R. So, totally 2R distance. So, this is also a 2R distance. Okay. As well as here to here, it is 2R distance. 2R distance. So, 1, 2, 3. So, to visualize, we are seeing 3 nearest equidistant neighboring atoms to this particular atom. But inwardly, there is 3 more atoms which are nearest equidistant place. So, as to this atom, inversely have another atom which is at 2R distance. That is, the atom is this one. To this atom, the nearest neighboring which are at 2R distance is this one, first one, the second, third. Suppose I am taking 3, we are counting 1, 2, 3. 3 nearest neighboring atoms we are seeing through this diagram. So, let's think that we are taking cube. So, in this cube, so it is one of the unit cell. So, this unit cell is a building block of a crystal structure. So that there is more number of blocks will be there along translational repetition. So, at left side, right side, above, there is unit cells. So that there are more unit cells in the crystal system or crystal structure. So here this is a block. Again above there would be another unit cell, and besides there is another unit cell. Like that, more number of unit cells are attached to this unit cell. So, opposite to the third atom, this one is this one, which is fourth atom at 2R distance. And while taking this second atom inversely, so opposite to this atom, there is one more nearest neighboring atom. This is also at 2R distance, which is opposite to this atom, and to this atom inversely there is another neighboring atom which is at 2R distance. So now we can count how many number of atoms are there in the nearest equidistant place. So 1, 1, 2, 1, 2, 3, and opposite to these three atoms, we have 4, 5, and 6. So the coordination number is 6 in the unit cell. That's why here Each corner atom has 4 neighbors. Each corner atom has 4 neighbors in the same plane. One is vertical above and one immediately below, giving total of 6 nearest neighboring atoms. So, we can take example for this simple cubic crystal structure. So, copper, Argentina are as best examples for this type of crystal structure. So, characteristics of a cubic unit cell. So, the atoms are like this. These are the atoms of one unit cell. So, the atoms be filled in this way. So, the edge length is A and half the distance between the nearest neighboring is R. So, here to here R distance, here to here R distance, and here to here is R distance. So, half the radius, half the radius to the nearest neighboring atom is atomic radius. So, if R is the atomic radius, now we are going to calculate the atomic packing factor in the simple cubic crystal. In that case, if R is the radius of the atom, A is the edge length of the cube side, then R is equals to A by 2. So, cube edge means here to here edge length. So, edge length is A and atomic radius here to here. We are taking like this atoms. So, here to here is R. So, that is it gives the radius R. So, here to here half the radius to the nearest neighboring atom R, atomic radius R. So, R is equals to A by 2. So, since each corner atom is shared by 8 surrounding cubes, so each cube comes to 1/8 of an atom. So, each corner atom in a cube. So, each atom, this is not completely an atom. So, this is shared. So in this unit cell, we can see only part of the atom. It is not complete atom. So the remaining part will be involved or will be in the other unit cell. So this complete atom is shared to different unit cells. So, each corner atom is shared by 8 surrounding cubes. 8 surrounding cubes means here at one side another unit cell, back side another unit cell, and front another, and left, like that. The unit cell will be repeated. Unit cell will be repeated in the crystal, so that each corner atom is shared with other cubes. So, each corner atom is shared by 8 surrounding cubes. So, each cube comes to 1/8 of an atom. So, each corner atom have 1/8 of an atom. Here also 1/8 of an atom. If we are taking cube, so one atom will be shared to 8 cubes, surrounding 8 cubes, so that here if you are taking one unit cell, each corner have 1/8 of an atom, share of 1/8 of an atom. So in this case, the cube contains 8 corner atoms. So one unit cell simply, we can say, one unit cell of a simple cubic contains 1 by 8 into 8 is equals to 1 atom. That is, in simple cubic, each corner atom be shared to 8 surrounding cube, so that here only 1/8 part only be in this unit cell. Remaining 7 parts will be in the other unit cells. So 1/8 of an atom. Here 1/8 of an atom. Here 1/8 of an atom. Here 1/8 of an atom. So each corner have 1/8 of an atom. So each corner. So 8 sides have 1/8 part. So 1 by 8 into 8 sides, it is equals to totally 1 atom. So in this case, if the unit cell has only 1 atom, then called as primitive unit cell. So the unit is called, or this unit is equal to the primitive cell. So in simple cubic crystal, the atomic packing fraction is equals to volume occupied by all atoms in the unit cell divided by volume of the unit cell, or else number of atoms into volume of an atom divided by volume of the unit cell. So number of atoms in a simple cubic is 1, because 1 by 8th part of an atom at each corner at into 8 sides. So at each corner, that is 8 corners, have 1/8 of an atom. So 1 by 8 into 8 is equals to 1 atom. So number of atoms is 1 into 4 by 3 pi r cube, which is the volume of the sphere. So 4 by 3 pi r cube divided by volume of the unit cell is a cube. So it is equals to 4 by 3. That is, it is equals to 4 by 3 pi r cube is equals to, into 1 by a cube. To 1 by a cube. So it is equals to 4 by 3 pi r cube divided by a cube. So here a is equals to 2r. So r is equals to, so it is equals to by 3 pi r cube. We can say r is equals to a by 2, because a is equals to 2r. A is equals to 2r. We can take r is equals to a by 2. Let's substitute a by 2 whole cube into 1 by a cube. So it is equals to 4 by 3 pi to a cube by 8 into 1 by a cube. So 4 pi a cube divided by 24 into 1 by a cube. A cube gets cancelled. So here we can get pi by 6. So this is not 2, this is 6. So pi by 6. So pi by 6 is equals to 0.52. So atomic packing fraction is equals to volume occupied by all atoms in the unit cell. So only one atom, how much volume it can occupy? 1 into 4 by 3 pi r cube by a cube. So it is equals to 4 by 3 pi a by 2 whole cube into 1 by a cube. So here r is equal to a by 2. Since a is equals to 2r, r is equals to a by 2. So instead of r, substituted a by 2. Okay. So it is equals to 4 pi by 3 into a cube by 8 into 1 by a cube. So a cube gets cancelled. 4 ones 4 6. So it is equals to pi by 6. So it is equals to 0.52. So that the atomic packing fraction is about 52%, and hence this structure is loosely packed because only 48%, that is 52% only atoms are packed in the unit cell. Remaining part is free only. So this structure is loosely packed. So only one element, which is a polonium, shows this type of structure at certain temperature region. So this is all about the simple cubic crystal. In the next session, we shall meet with another topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.